Okay, so today's session is about batch normalization, accelerating deep network training by reducing internal covariate shift. So let me just start with the paper details. Batch normalization is written by Sergey, Ioffe and Szegedy, and it's published in International Conference on Machine Learning. But right off the bat, I just brought something interesting. As you can see, the numbers on the Google score doesn't match. Don't match. I don't know why, but it seems that Google score is not that reliable. Yeah, I don't think they think about citations anymore, but it's interesting. Anyways, thank you. Outline. I'm going to talk about internal covariate shift, batch normalization, and the speed up that is happening in ImageNet training, and state of the art in ImageNet classification. First, let's talk about the motivation of this paper. First, the motivation is obvious: how to train networks faster and better. And that raises when we are dealing with saturation problem, as you can see in this figure. When we fall under that saturating zone, our gradients deal with vanishing gradient problem, and that's not a good thing, and that slows down the training. So what we want is to gradients to fall under safe zone, and that happens with batch normalization, and they try to do this with sigmoid and other saturating activations. So let me just mention some of the advantages of using mini batches first. And the first one is the gradient of the loss over a mini batch is an estimate of the gradient over the training set, whose quality improves as the batch size increases. The second advantage is that the computation over a mini batch can be more efficient than M computations for individual examples on modern computing platforms. And that brings us to the effect of changing input distributions. So our networks are always dealing with changing input distributions, and three strategies that we can deal with this problem is to have careful initializations, or we can have small learning rates, or non-saturating nonlinearity such as Ray loop function. But there is one problem. We have layers that need to continuously adapt to the new changes. And that is really difficult when the inputs are the outputs of a subnetwork. If you pay attention to these two graphs, if you have a network that starts with X and goes into activation function, that's not a big problem for us. But when the input is the output of a previous layer, that makes it really difficult because it's always changing. And that's the covariate shift problem, basically. Covariate shift problem is the phenomenon where the training and the tested distributions are different. And this reduces the generalization performance of the model. So we all know that if you have a network with just one layer, normalizing inputs can speed up learning. And that's when, imagine if we have two inputs, one of them is not the same scale as the other. That makes the gradient to be really slower. And if we scale them, it will increase our performance and our speed. So internal covariate shift arises when they actually introduce another problem. So when we have deeper networks, we are dealing with internal covariate shift, and that's because our hidden layers have inputs that are always changing. So imagine in this network, we want to train we are considering the third layer, and we don't know about the first two layers. But what is happening for the third layer just sees WB and A's in that transformations that it's dealing with. And these A's are always changing because when we are training, W, B are always changing. And that makes the function to be dynamic. And So if we compare to this one, we can see that inputs in this network are not always changing, but for the hidden layers, we have inputs that always change. That's the internal covariate shift. That makes the training really slower and makes our accuracy to become lower. One of the things that we can do is to use domain adaptation, which is a special case of transfer learning, but I'm not going to go deep into that. But they mention it in the paper, and I just brought it here. So imagine we have two functions. First function is the function of the other. And when the parameters in one function changes, the other function also changes. That's what's happening in the internal covariate shift problem. So solution to internal covariate shift is to make the distribution of nonlinearity inputs remain more stable. And that's what batch normalization is trying to do. And they suggest that normalize each activation. But also we want to the normalization to participate in the gradient optimization. So for that, natural idea is to compute expected value and variance as running averages. But that blows up the model, and it seems that it doesn't work, and it's not practical, because gradient optimization ignores the dependence of expected value and variance on the model parameters. So they actually come up with this idea to change the model architecture, not the optimizer. So I brought these two figures. What they are trying to do is to, if we consider the left figure, we have the Z1 and Z2 if we have 2 dimensions, and they have some values. And the thing that we try to do is to change it in a way that distribution stays the same, like mean and variance stay the same. And that would actually be the main idea behind batch normalization. We can have a mean 0 and variance 1, but not always it's going to be that way, because we have gamma and beta that control that property for us. So let's talk about the implementation of batch normalization. What batch normalization actually offers are too many points that I brought them here. Normalization step that fixes the means and variances of layer inputs, makes the weights deeper in the network more robust to changes to weights earlier in the network. So if we change a weight, let's say in the first layer, it's not going to affect a lot the 10th layer. And it reduces internal covariate shift, and that speeds up the learning of deep nets. And also, it reduces the dependence of gradients on the scale of parameters or their initial values. So that's why we can have higher learning rates without the risk of divergence. And actually, in their experiments, they got learning rates up to 30 times more than the baseline, which is in that experiment's inception model. I'm going to explain about it in my next slides. So the next point is that it regularizes the model and reduces the need for dropout, and also it's avoiding saturated mode, which I explained, even with saturating nonlinearities. And the last point is that it sets state-of-the-art in large-scale image recognition. Okay, so let's talk a bit about batch normalization as a regularization or regularization. So they say that each mini-batch is scaled by the mean and variance computed on just that one mini-batch. So each mean and variance has some noise in it that is being added to each hidden layer's activations, just like dropout. And this has a slight regularization effect. They actually removed the dropout in the paper, but based on what I read and based on the experts like Andrew and G, they suggest that it's not a good idea to actually remove the whole dropout. And the best way is to balance it in a way that both of them work. And they say that it's not a good idea to use batch norm as a regularizer. But the paper suggests that if you remove the dropout, it performs the best. So, and also one way to balance it is to, for instance, increase the batch size. If we increase the batch size, we will have less regularization, and then we can use dropout to use the regularization effect of the dropout. Okay, so let's talk about the formulas and also the algorithms. So batch normalization uses mini batches statistics, not the whole population. And in this figure, we can see that they calculate the mini batch mean, mini batch variance, and they normalize it and get to this x hat. And they use that x hat in the final equation to scale and shift and get to the yi. I'm going to explain about it in the next slide. So if we have a normal network without batch normalization, what we do is to have x1, w1, v1, and we calculate the linear function and get z1. And as you can see here, and we feed the z1 to the activation function and get a1, and then the rest. But what happens in batch normalization is as this actually the functions that are brought here, the notations. We have x, and then we calculate mu and variance, and we have w1, v1. We get z1, but now we have a middle stage here, middle step, which is batch normalization with gamma and beta. So what we do is to calculate the previous function, and then feed that to, and then get our z hat. Just for simplicity, I brought these notations. It's not the one that is in the paper. We calculate z hat, and then we get to a1, which is basically the function of z hat, not z. So, and also the rest of the network is just repeating this process. Okay, so backprop with batch normalization. What happens when we want to backprop the network? What we have is basically we have gradient of the loss function over yi, which uses the gamma and beta, and then we have gradient of the loss over x hat, then variance, and then mean, and we get variance of the loss over xi. One thing to note is that for the parameters that we have, WB, beta, gamma, one thing that happens is that B is going to be non-effective because we have a subsequent mean subtraction, and that makes B to be non-effective, and we can put it to permanently 0 or just remove it from the equation. That's what they did in the formulations. And at the end, we have inference with batch normalization. So for the test stage, we don't have mini batches. Basically, it's just one batch. We don't have batch at testing stage, basically. And we replace the batch statistics with population statistics. And ideal solution is to have a mu and sigma calculated using the whole training data set. But turns out it's not a good idea to do this. And the practical solution is to compute the exponentially weighted and moving average of mu and sigma, variance of the mini batches during training. And I brought this figure. When we are doing that, the accuracy of mu is going to increase as we update the mu's. And what we get is a simple, I put it this way because it's easier to understand. There was this algorithm that was pretty much a little bit complicated, but it's not that complicated. I just brought it like this to make it more simple. So for t equals to 1 to number of mini batches, we compute the forward prop on x, and then in each hidden layer use batch normalization to replace z with z hat, and we use backprop to compute the what was that, dw, d beta and d gamma, and then update the parameters. Also, one thing to point out is that batch normalization works with darkness prop, momentum, or Adam or other optimizers out there, and that's a good quality of it. So let's talk about the convolutional layers. There is a bit difference with convolutional layers. What they did is to have different elements of the same feature map at different locations, normalized in the same way. And normalized over mini batch examples and nodes. Also normalization before nonlinearity. basically the whole batch normalization is before nonlinearity. There are studies that are doing this after nonlinearity, but these guys say that this is the best way to do it. And also, it's invariant to scale of W, and that's a good a property. So the last one is that we learn parameters per feature map rather than per activation. Okay, let's get to experiments. They experimented on MNIST, which are 28 by 28 binary images. They used 3 fully connected layers plus softmax and 100 logistic units per hidden layer. And the W is initialized to small random Gaussian values. And the last hidden layer is followed by a fully connected layer with 10 activations, which are 10 digits, and cross entropy loss. At the end, distribution of inputs to a typical sigmoid evolving over 50K steps and 60 examples per minibatch is these 3 figures. The first one suggests that with batch normalization, our accuracy increases rapidly and gets to a higher accuracy. But without batch normalization, it takes time to get to that accuracy, but also it doesn't get to that accuracy, basically. The second figure is without batch normalization, and that's basically the evolution of input distributions to a typical sigmoid over the course of training. And we can see that it fluctuates a lot, and that slows down the training. And it's not stable, basically, and that's basically the effect of internal covariate shift. But with batch normalization, we can see that it's really stable here. These are 15 percentile and 50% percentile and 85 percentile. And that solves the reduces, basically, not solve, it reduces the internal covariance shift. So the next experiment is ImageNet classification, which they are using Inception, deep convolutional ReLU model, basically. And batch normalization is applied to every convolutional layer, which has the extra cost of about 30% per training step, and does not change the cost of inference. And also they are using distributed or asynchronous Szegedy with momentum as an optimizer, but any mini-batch based optimizer can be used. The size of the mini-batches are 32. And they suggested some methods to actually accelerate the batch normalization networks. First one is batch norm enables higher learning rates, and basically they increased it 30 times more than the learning rate of the original inception, which I think it was 0015. And the second point is that they are removing dropout, and that improves validation accuracy. Shuffle training examples more thoroughly, and also the next one is reduces the L2 weight regularization, and the next one is accelerates the learning rate decay, which is really cool. I think it was 6 times more than Inception, and it removes the local response normalization, and also the last one is to reduce the photometric distortions. And the results are as follows. You can see that in the left here, Inception model, basically the line, the black line, takes a long time to get to a high accuracy, and the accuracy is basically 72.2%, and it takes 31 times 10 to the power of 6 steps to get to that accuracy. But batch normalization baseline, which is the red dashed line, is gets to that accuracy or even higher with 13.3 times 10 to the power of 6. The next thing is that batch normalization with 5 times the learning rate of the Inception is getting to a higher accuracy with really lower steps, 2.1 times 10 to the power of 6. And it gets to 73% accuracy, and that's really interesting to see. But one thing to point out is that when we are using batch normalization with 30 times the learning rate of Inception, actually an interesting thing happened, and that's we get to a higher accuracy. That's basically this blue third line. We get to a higher accuracy, but slower than the 5 times learning rate. And that's the best thing that they got there. And basically, that's when they are saying that it's a good idea to study that more to see why this happens. One interesting thing to also mention is that although Inception can't use sigmoid in its activation function, they used sigmoid and they got to 69.8% accuracy, which is really interesting. But as you can see, they don't put steps here because they didn't get to 72.2% accuracy. So they trained something that couldn't done before with Inception, and that's really cool. All right, the last one is to point out the state-of-the-art classification, ImageNet classification, which is basically they used in ensemble method to get to a better accuracy than the MSRA ensemble, which we studied, I think, last week, and that was 4.94. And as you can see, Batch Normalization Inception ensemble uses 6 models with 144 crops, and that's the best results that they got. But I saw in their presentation that they mentioned that they got even better results, and that was 3.58% top 5 error with 4 models and 144 crops. And that's basically 0.01% behind the winner, about that amount. That was interesting to see. Okay, so I get to my summary. We are reducing the internal covariance shift speed, and that speeds up our training. And batch normalization uses mini batches, mean and variance. And we can use higher learning rates, less dropout, easier initialization, and can have state-of-the-art in ImageNet classification. And for the usage, it is implemented in many open source deep learning frameworks. And if we go to TensorFlow, like if you write TensorFlow.nn, you can use batch normalization easily, just that 3 words. And it's compatible with your favorite optimizer, and successfully used in many labs. And also it's been used on images, speech, RNNs, natural gradients, adversarial training. But about RNNs, I read in an article that it's not a good idea to use this in RNNs, and they brought their own reasons. So I also brought this for discussion part. For the shortcomings, it's unstable when using small batch sizes, and it leads to increased training time. They also state that, but what we saw here, it was that it's better with Inception. So, and gets different results in training and inference. It's not good in online learning. And also for the alternatives, we have layer normalization, instance normalization, group normalization, and synchronous batch normalization. And these are the references that I used. Thank you for your attention.